Alrighty, so today is the second bit on Thevenin and Norton equivalent circuits. The in-class assignment has two problems, the first of which can be solved just by directly applying Thevenin's theorem and Norton's theorem. Take out the resistor RL and perform the appropriate circuit analysis. There is literally no difference except that you cannot determine the Thevenin resistance directly. If you wanted to do that, you would have to use a test source method, which I believe I went over in the video lecture, but we're going to look at problem 2, which is going to require the use of a test source method because it does not have any independent sources in it. So once we finish this guy up, then we'll take a look at the lab. Alrighty, so tons of noise. Alrighty, so our test source method is effectively just exploiting good old Ohm's law. What it says is that I can put a test voltage across my network of interest, measure the current flowing into my network of interest, and the Thevenin resistance will then be simply V test divided by I test. Or I could change the circuit slightly and I could apply a test current I test and measure a test voltage across the network V test, and this exact same relationship would give me my Thevenin resistance. So that's just literally using Ohm's law, right? Ohm's law stated that if we know the voltage drop over a network or series or combination of components, and we know the current flowing into the network, the ratio of those two quantities is the equivalent resistance. That is exactly what we're doing right here. All right, so the first thing that we want to do is determine whether or not we want to use a test current source or a test voltage source. You can absolutely get the correct answer using either, but a smart choice early on might make things significantly easier. So which, just looking at this guy, does anybody have any idea of whether we should use a test current source or a test voltage source? So Mr. Garrett here says that we should use a test voltage source. How many of you agree with him? I see a couple of hands. How many of you think we should use the test current source then? Probably everyone else, roughly, right? So the class is split about halfway. So if we use a test voltage source here, the problem wouldn't be particularly difficult. But if I use a test current source, let's just call it 1 milliamp for the sake of argument. What does that tell me about the voltage Vx? Yeah, so it's 1.6 volts right off the bat. Because I chose a current source here strategically, I know what that voltage Vx is now. So my dependent source circuit no longer behaves like a dependent source circuit because I know inherently what the controlling variable is, right? So Vx is 1.6 volts, 1 milliamp times 1.6 kilo ohms is 1.6 volts. So this guy right here is then simply 3.2 volts, and we now don't have to worry about coming up with dependent relationships, right? Everything is well behaved. So that's what a good choice on a test source can do to a lot of problems. Now, sometimes it won't work out to be this easy. This one was constructed specifically to illustrate that making a good choice in these type of circuits can vastly simplify the problem. All right, so our goal now is to figure out what this voltage V test is. So how would you all consider we should approach determining that voltage? Anybody got any ideas? So the suggestion here is to use source transformation techniques to make it a single loop circuit. We could do that. Let's see, that'd be 1, 2, 3 steps. Then we would have to multiply 1 milliamp times the total resistance that we'd see. We wind up having to do a Kirchhoff voltage law loop is what it would work with. So 4 steps with that method, if I'm counting things correctly in my head. So what if we did nodal? This is an unknown voltage, V test. This is an unknown voltage, let's call it VB, and this other guy is a known voltage. Would that be a particularly difficult system of equations to develop and solve? 2 equations, 2 unknowns, right? So I think taking 4 steps versus setting up a simple system, I'm going to go with the simple system. So let's do KCL at our test source node first. So we're looking right here, current directed to the left and current directed to the right. So we would have negative 1.6 milliamps plus V test minus VB divided by 1.6 kilo ohms is equal to 0. That's effectively already telling us exactly what we know. And so what I mean by that is we know the voltage drop V test minus VB is 1.6 volts already, so it's effectively saying 1.6 milliamps is, sorry, not 1.6, 1 milliamp. I apologize for that. Getting myself mixed up here. It's telling us the current flowing through that resistor is 1 milliamp, effectively what's happening. So that's really nothing particularly new. KCL at node B would give us VB minus V test divided by 1.6 kilo ohms plus VB over 8.4 kilo ohms plus VB minus 3.2 volts divided by 7.5 kilo ohms is equal to 0. So we've got 2 equations, 2 unknowns. So let's solve for V test and VB. And for those of you that are uncomfortable with nodal analysis, I highly suggest you practice it because one of the last topics that we're going to see before we move on to the exam 3 material is, analysis of operational amplifier circuits, which rely heavily on nodal analysis. In fact, I don't know that you can actually use mesh analysis on them to be able to apply the rules correctly. So practice your nodal analysis techniques. All right, so let's go to our 2x2 system solver. So our coefficient for V test in the first equation is 1 over 1600. Our coefficient for VB is negative 1 over 1600. And when we move the constant over to the right-hand side of the equal sign, that's going to be 0.001, where I'm putting everything in terms of ohms and amps and volts. All right, for our second equation, V test has a coefficient of negative 1 over 1600. VB has a coefficient of positive 1 over 1600 plus 1 over 8400 plus 1 over 7500. And our constant term, when we move it to the right-hand side of the equal sign, is going to be 3.2 volts divided by 7500. Why did that give me? Well, I get V test as 7.253 volts and VB is 5.653 volts. So if we look at our equation for the Thevenin resistance, it's 7.253 volts divided by 1 milliamp is going to be what? 7.253 kilo ohms, which is exactly what we get here. Now, just to show you that we could do this with a test voltage source and get the exact same result, let's repeat this. So now I'm going to apply a 1 volt source. So does the magnitude of the voltage source or the current source or anything like that matter? Would it have changed anything if I had used a 1 amp source versus a 1 milliamp source? It does not, because of the homogeneity principle of linearity, right? If I scale my input, I scale my output, right? And so all of my currents and stuff would have been increased by a factor of 1,000. My voltage then that we determined at the output would have been scaled by a factor of 1,000, but that same voltage of 7.253 kilovolts divided by 1 amp would have still given us an answer that was 7.253 kilo ohms. So I'm arbitrarily choosing 1 volt, 1 amp, things like that. You could choose 37.5 if you wanted to. Doesn't particularly matter what you choose. You're going to get the exact same answer. All right. So now I don't know what Vx is, so I'm going to have to go through this in a slightly different way. And my goal is to find this current I test. So how would you guys suggest we do that? Mesh. I'm trying to find a current. This is a pretty simple system. Mesh should work out pretty easily. 2 equations, 2 unknowns, and the controlling variable. So let's call this guy I1, which is going to be the exact same thing as I test. And this guy over here, and we can leave it as I test. That'll be fine. Actually, no, I don't want to do that, because that would, the reason why I'm hesitant on calling that whole mesh I test is because I test doesn't flow down through the 8.4 kilo ohm resistor, and I would not want to confuse you guys on that point. So we're just going to call it a completely separate mesh current. Alrighty, so there are no current sources, so we can just simply do KVL. So we'd have -1 volt plus 1.6 kilo ohms times I1 plus 8.4 kilo ohms times I1 minus I2 is equal to 0. KVL at mesh 2 gives us 8.4 kilo ohms times I2 minus I1 plus 7.5 kilo ohms times I2 plus twice Vx is equal to 0. And lastly, we're going to have to define our controlling variable Vx in terms of our mesh currents. So Vx is going to be what? .6 kilo ohms times I1. Thank you, man. All right, so we could do substitution, but this is just 3 equations, 3 unknowns. I'm just going to put it in my calculator as is with Vx as my third variable because I'm too lazy to do the substitution. So from this, we'll get a mesh current I1, which is exactly equal to I test, a mesh current I2, and a voltage Vx. All right, so 1600 plus 8400 is my coefficient for I1. Negative 8400 is my coefficient for I2. 0 is my coefficient for Vx. Constant term is +1. My next equation, I have negative 8400 I1, 8400 plus 7500 I2, and 2Vx. My last equation, I have 1600, sorry, I should 0 for my constant term, 1600 I1, 0 I2, negative 1 Vx. If we move it over to the right-hand side, that's where that negative sign is going to come from, so that we have variables on one side of the equal sign, constants on the other. 0 is my constant value, and when I solve for I1, I get 137.877 microamps. Make sure, yeah. For I2, I get 45.092 microamps, and for Vx, I get 220.603 millivolts. R7 is V test divided by I test, which is 1 volt divided by 137.877 microamps. Is 7,252.83 ohms, or 7.253 kilo ohms. We'll get the exact same result. Would it matter if I change the sign on the polarity of my voltage source or anything like that? Also no, right? So when you use the test source method, you really just need to pick either a voltage or a current and then run with it, and you're going to get the right answer regardless of whether your choice made the problem easier or not. One thing that I do want to point out, in this first problem here, we could use the test source method to determine the Thevenin resistance of this network directly, instead of using the ratio. The Thevenin resistance is V Thevenin divided by I Norton. Whenever you're using the test source method, you have to be looking at a dead network, meaning all of the independent sources are off. So that rule still applies from Thevenin and Norton's theorem. So this guy is a dependent source, which means it has to always be on, okay? That's something that I noticed a lot of you guys on your exam struggled with when applying superposition, as you tried to turn off the dependent source and then couldn't get the correct answer, and it's because you were applying the superposition theorem incorrectly. So the dependent sources always stay on. All right, any questions about this example problem that we've worked two different ways? Pretty much the only two ways that it can be done, actually. Alrighty, so today is the second bit on Thevenin and Norton equivalent circuits. And these today have dependent sources in. So if we look at our first problem here, which I'm not going to work on actually, effectively you would use the exact same circuit analysis techniques that we discussed last week. So you would take this resistor RL out and then measure the open circuit voltage of V Thevenin, nothing different than what we did. Then you would short circuit it and find the short circuit current I Norton, and then the ratio of those two quantities would be used to find the Thevenin resistance because of the dependent source. Now in our second example problem, which we're going to look at today, it allows us to determine the Thevenin resistance of a circuit containing a dependent source directly. Okay, and it's done by using what's called a test source method, which is really nothing more than applying Ohm's law to the network as a whole. And so what I mean by that is we have two options. We can hook up a test voltage source, V test, and measure the current flowing into the network. So if we know the voltage drop that we've applied over the network and we measure the current going into the network, the ratio of those two quantities is R Thevenin. So R Thevenin is V test divided by I test using Ohm's law. Alternatively, we could apply a current source, I test, and measure the voltage drop over the terminals of the network. And we would find that that exact same ratio, V test divided by I test, gives us the equivalent resistance of that network as well. That's how Ohm's law was determined experimentally. You apply a known voltage to the terminals of an unknown material with unknown properties, measure the current that flows through it, and that tells you what the resistance of that thing is. So with that in mind, we are going to apply our test source method to this particular circuit and determine the Thevenin equivalent resistance. We're going to work it both ways to show you how a smart choice, as it were, on what kind of test source to use may simplify the circuit greatly. So which one do you guys want to do first? The test voltage source or a test current source? Test voltage, all right. What test voltage should I use? 1 volt, all right. So here's another question for you guys. Does it matter what test voltage I use? No, because of the homogeneity property of linearity. I can use a 1 volt source or a 500 volt source. I can put positive polarity on top or positive polarity on bottom. None of those things matter. I am going to get the exact same Thevenin resistance every single time. So using a 1 volt source like so, we are going to then try to measure this test current. So how do you feel we should go about determining that quantity? What circuit analysis technique or combination of techniques could we use here? Yeah. So KCL by itself or KVL by itself probably isn't going to cut it. And why? So KVL by itself isn't going to cut it because there's there's 3 different paths that we could choose. So we could develop some KVL relationships, which would be mesh analysis. Since there are 1, 2, 3, 4 nodes, KCL by itself isn't going to work, but we could use all of them together and get node 1 analysis. All right, so you're suggesting mesh. That's what I would use here as well, because it's going to be a simple 2 equation, 2 unknown system, because there's just 2 meshes, right? So let's call this guy mesh 1, and this guy mesh 2. And so we're going to write a Kirchhoff's voltage law equation around mesh 1. Starting at the bottom left-hand corner, we would see negative 1 volt plus 1.6 kiloohms times I1 plus 8.4 kiloohms times I1 minus I2 is equal to 0. Around mesh 2, we would see 8.4 kiloohms times I2 minus I1 plus 7.5 kiloohms times I2 plus twice Vx. And now that we've introduced a third variable, excuse me, Vx, we need to put that in terms of our mesh currents as well. So our other equation is going to be Vx is equal to what? Absolutely correct. 1.6 kiloohms times I1. So we got 3 equations, 3 unknowns. My calculator can handle that, so I'm going to be lazy and not perform any substitution here. And so let's find out what those guys are going to be. I1, which is exactly equal to I test, I2, and lastly, Vx. So the coefficient for I1 is 1600 plus 8400. The coefficient for I2 is negative 8400. The coefficient for Vx in my first equation is 0. And then when I move the constant value term over to the other side of the equal sign, that gives me positive 1. For my next equation, my coefficient for I1 is negative 8400. My coefficient for I2 is 8400 plus 7500. And my coefficient for Vx is 2. Constant term is 0. And then in my third equation, my coefficient for I1 is positive 1600. The coefficient for I2 is 0. The coefficient for Vx is negative 1. So I'm just moving Vx from the left-hand side of the equal sign to the right-hand side because it's a variable. And then my constant term is 0. And when I solve these guys, I get 137.877 microamps for I1, 45.092 microamps for I2, and lastly, 220.603 millivolts for Vx. So using my equation, R Thevenin is V test, which was 1 volt, divided by I test, which is 137.877 microamps. I get 1 over X is 7,252.830 ohms, or 7.253 kilo ohms, which exactly matches my expected answer. So not particularly difficult there. Anybody have any questions about the measurement analysis technique that we employed here to solve this one? All right. So now let's see what happens if we had applied instead a test current. And I'm choosing a milliamp test current source here, just because my resistors are kilo ohms. And so I know that that's just going to give me volts. So if I put like a 1 amp source, then I'd be dealing with kilovolts, and I don't want to do it. It's all the exact same thing. I just don't want to carry around an extra prefix on my units here. So using a current source in this case, that lets me effectively determine what the voltage Vx is, or it lets me set it, right? So if I use a 1 milliamp current source, what's Vx? 1.6 volts, which means this dependent current or voltage source isn't really dependent anymore. I mean, it is, but we know how much voltage it's going to be supplying, 3.2 volts, right? So we've taken away some of the complication by choosing a current source in this case, right? So that's what I was talking about earlier about, either way is going to work and give us the right answer. But if we make a smart choice on the type of test source that we use, we might eliminate some of the difficulty of analyzing the circuit. All right, so my goal now is to determine this quantity, V test, and I'm going to do so by using nodal analysis. I want a voltage, so I'm just going to use nodal analysis to make things pretty easy here. I'm going to call this guy VB, and this node I'm just going to use as my test voltage because it's the exact same thing as I've defined my test voltage. The difference in those two terminals, my negative terminal is connected to ground. So this V test and this V test represent the exact same quantity. So hopefully not any ambiguity there. All right, so if I apply Kirchhoff's current law at the V-test node, what I get is -1 milliamp plus V-test minus VB over 1.6 kiloohms is equal to 0. And if I apply KCL at node B, I get VB minus V-test divided by 1.6 kiloohms plus VB divided by 8.4 kiloohms plus VB minus 3.2 volts, that does not look like a V, divided by 7.5 kiloohms is equal to 0. Two equations, two unknowns, fairly easy to solve. So let's solve this system for V-test and VB. All right. Anybody have any questions about the KCL equations that I wrote or anything like that? Anything seems straightforward? Anybody got beef with me regarding this problem? Sure, after your grades come out, you'll have beef with me over the test, and I will meet you in the parking lot as needed. All right, to get my butt handed to me, I'm sure. All right, when Davis finishes Moodle, so there will be a thing that says, like, if you go to the grade book, it'll say exam 1, and then it'll have your score. All right, so solving this system of equations. Two equations, two unknowns. So V-test is going to be my first variable, so I have a coefficient of 1 over 1600, and for V-test, -1 over 1600 for VB. When I move my constant 1 milliamp over to the right-hand side, I'm going to have 0.001. So I'm putting things in terms of amps as opposed to milliamps, and ohms as opposed to kiloohms, so that my units come out to be volts because I'm looking for voltages. On my second equation, my coefficient for V-test is 1 over 1600. My coefficient for VB is 1 over 1600 plus 1 over 8400 plus 1 over 7500. And my constant term is going to be 3.2 divided by 7500. The same syntax there as last time for some reason. And I get 7.253 volts and 5.653 volts respectively. Now R Thevenin is 7.253 volts divided by 1 milliamp is what? 7.253 kiloohms. So we worked this problem using two wildly disparate methods, where we in one case we applied a voltage source, and in the other case we applied a current source, and we came out with the exact same number. So the only thing I really feel that I need to point out further is that we could have used the test source method here in this first problem as well to calculate the Thevenin resistance directly. The only thing that we need to make note of is that whenever we're calculating the Thevenin resistance directly, we need to be looking at a dead network, meaning all of our independent sources are turned off. So that still holds true even with dependent voltage sources or dependent current sources in the mix. We always have to be looking at a dead network. For this guy down here, there were no independent sources to turn off to begin with, so that's why we were able to just jump right in. If we wanted to apply that approach to this guy, we need to have to short circuit that guy and open circuit our current source and then apply the test source method. Okay, any other questions on Thevenin and Norton equivalent circuits and all that jazz? Hopefully between the examples and the 2 videos and all that stuff, should be good to go. All right, so that's going to be the first couple of problems on your upcoming exam 2 that's in a couple of weeks or whatever. So this is where the exam 2 material starts.